A 24-foot cast-iron monster from 1911 sat abandoned in a Detroit salvage yard, tagged for scrap at $12,000. 3 months later, that same machine removed 8,000 pounds of hardened steel in a single weekend, a job that had just killed two $400,000 modern CNC planers. How did a machine built, when the Titanic was under construction, outperform equipment designed with a century of additional engineering knowledge? Before we continue with the video, if you're listening right now, help me prove something wrong. My wife said I wouldn't even reach 1,000 subscribers, but I believe stories about old machines like this deserve to be heard. Help me show her that these videos matter. Please subscribe to our channel and let's keep these old machines' legacies alive. November 2024. James Reeves stood in the fabrication bay at Great Lakes Heavy Industries, staring at a problem that had already cost his company $340,000. Two Waldrich Coburg CNC planers sat silent, their control systems fried after attempting to machine a massive turbine housing for a hydroelectric retrofit project in upstate New York. The part was a nightmare, a 16-foot-long casting of manganese steel, heat-treated to 450 Brinell hardness, harder than armor plate. The customer spec called for removing 6 inches of material across the entire top surface, holding flatness within 5/1000ths across the full length. Simple geometry, brutal execution. First machine made it 40 hours before the ball screws seized, James explained to his plant manager, Sarah Chen. Cutting forces were just too high. Second one lasted 3 days before the servo drives overheated and took out the main controller. He pulled up the repair estimates on his tablet. Waldrich wants $85,000 per machine to replace the damaged components, plus 8 weeks lead time we don't have. Sarah walked around the massive casting, running her hand along the rough surface where the CNC had failed mid-cut. The interrupted passes left ridge patterns that would need grinding smooth before they could even attempt another machining operation. What about outsourcing? Cleveland has that new Giddings and Lewis gantry mill. James shook his head. Called them yesterday. They won't touch manganese steel at this hardness. Too much risk to their equipment. He showed her a list of decline quotes from every major job shop within 200 miles. The work was simply too demanding for modern equipment designed around high-speed cutting of easier materials. The contract included penalty clauses that kicked in after 60 days, $15,000 per day for late delivery. They were already 12 days behind schedule with no clear path forward. Scrapping the project meant eating $680,000 in costs, plus losing a customer who represented 15% of their annual revenue. There's one more option, said Tommy Breslin, the shop's oldest machinist who had been listening quietly from the doorway. Probably think I'm crazy, but hear me out. He pulled out his phone and showed them a photograph of an enormous machine tool that looked like it belonged in a museum. Cincinnati 24-foot planer. Built 1911, sitting in a salvage yard over in River Rouge. Owner's been trying to scrap it for 2 years but can't find anyone willing to cut it up. Sarah studied the photograph, noting the massive cast iron construction that dwarfed even their largest machine tools. You're seriously suggesting we try to machine aerospace-grade steel on a 113-year-old antique? But what if that antique was specifically designed to do what modern machines couldn't? The salvage yard occupied 6 acres of cracked concrete and rusting industrial equipment on the edge of the Detroit River. Tommy led them past rows of dead stamping presses and obsolete power hammers until they reached the back corner where the Cincinnati planer sat beneath a corrugated metal shelter. The machine was staggering in its physical presence. The bed stretched 24 feet long, cast as a single piece of meionite iron that had to weigh 40,000 pounds. 4 massive columns rose from the bed corners, supporting a cross rail that could position cutting tools anywhere across the work envelope. The entire structure was covered in decades of oil, dust, and the patina of abandonment. Herb Kowalski bought this from a closed Ford supplier back in 2018, Tommy explained, introducing them to the yard owner, a weathered man in his 70s who approached carrying a grease-stained ledger. Paid $8,000 for it, figured he'd part it out. Problem is, nobody wants parts from a planer anymore. Everything's CNC now. Herb flipped through the ledger, showing purchase records and attempted sales. Had 3 scrappers look at it. They all said the same thing. Too much work to cut up, not enough value in the iron. Been trying to give it away just to get the floor space back. He patted the machine's column with genuine affection. "Shame, really. This beast was machining gun mounts during World War I. Saw every war since. Now it's just taking up space." James climbed onto the bed, examining the ways that guided the massive table. Unlike the ground linear guides on their failed CNC machines, the planer used hand-scraped surfaces, thousands of tiny oil pockets visible even under the accumulated grime. The table itself was a 12-foot-long slab of cast iron riding on those scraped ways, driven by a rack and pinion system that looked agricultural in its robustness. Sarah studied the tool head assembly, noting the simple mechanical systems that positioned cutting tools. No servo motors, no ball screws, no electronics at all. How do you even control something like this? "You don't control it," Tommy replied, cranking one of the massive hand wheels that traversed the cross rail. "You command it. Operator sets the depth, sets the feed rate, engages the drive, and the machine does what it was built to do: remove steel." He showed them the change gears that selected feed rates, ranging from a crawl to surprisingly aggressive cuts. Cincinnati designed this for heavy interrupted cuts in the hardest materials they could find. Manganese steel, tool steel, anything that would destroy lighter machines. Herb produced a ring of keys and opened the electrical cabinet, revealing knife switches and motor starters that belonged in a power plant. "Motor's still good. Had an electrician test everything last year, mechanically sound, just needs cleaning and oil." He quoted them a price that seemed impossibly low. "Take it for $12,000, includes me hiring riggers to load it on your truck." James did the math silently, less than 15% of what one CNC repair would cost, and they needed to fix 2 machines. But the real question wasn't cost. Could a machine built when Taft was president actually outperform equipment designed with 21st century technology? Moving 40,000 pounds of cast iron required more faith than engineering. The riggers arrived at Great Lakes Heavy Industries with a 60-ton crane and expressions that suggested they'd seen this movie before, another shop buying old junk that would never run. Tommy directed placement with the confidence of someone who had spent 40 years working around heavy iron. The planer's bed went on to foundation pads he had positioned according to the original Cincinnati installation manual, a document he'd found archived at the Detroit Public Library. "These old builders understood foundations," he explained, as workers grouted the pad's level. "They expected the floor to move, the building to settle. That's why the bed sits on 4 independent pads with adjustment screws. You level it once and it stays level." The cleaning process revealed the machine's true condition. Beneath the cosmetic grime, the ways showed minimal wear. The hand scraping that had been performed in 1911 still retained its oil pockets and bearing contact patterns. James ran a precision straight edge across the bed's length, checking with a dial indicator that showed less than 0.003 deviation across 24 feet. Modern machine tools claimed tighter tolerances, but they achieved it with ground surfaces that wore rapidly under heavy loads. "See these flaking patterns?" Tommy pointed to the microscopic texture visible on the cleaned ways. Master scraper named Heinrich Stein did this work at the Cincinnati factory. Each one of those tiny valleys holds oil. When the table moves, it's floating on a film of lubricant that never breaks down. He demonstrated by cranking the table by hand, 12,000 pounds of iron gliding smoothly across the bed with surprising ease. Sarah coordinated the electrical work, bringing in a motor specialist who understood 3-phase power systems from the era before variable frequency drives existed. The main table drive was a 40-horsepower DC motor with a wound armature the size of a beer keg. "These old motors make torque like a diesel locomotive," the electrician explained, measuring insulation resistance that still tested within specification. "No fancy electronics to fail, just copper, iron, and electromagnetic fields that follow laws of physics unchanged since Maxwell." The toolhead presented the biggest question mark. It used a simple clapper box system. The cutting tool mounted in a holder that could pivot backward if it encountered an obstruction, protecting both tool and work from catastrophic impact. Tommy installed carbide-tipped tools designed for interrupted heavy cuts, the kind that would shatter in a high-speed CNC spindle but thrived under the planer's slow, powerful strokes. 3 weeks after purchase, the Cincinnati planer was operational. No computer programming, no electronic calibration, no servo tuning. Just mechanical systems doing what they had done for 113 years. James stood beside the machine as Tommy engaged the table drive for the first test run, listening to the deep rumble of the DC motor as the massive table began its traverse. The question everyone was avoiding: what happens when this museum piece meets the steel that killed 2 modern machines? They positioned the turbine housing on the planer's table at 6 a.m. on a Saturday morning using a 20-ton overhead crane and Tommy's practiced eye for work holding. The casting weighed 14,000 pounds, too heavy for the failed CNC machine's tables, but well within the planer's capacity. Tommy indicated mounting points where the casting's geometry would resist cutting forces without complex fixturing. "Old-school clamping," he explained, using massive cast-iron blocks and bolt-down clamps that looked like they could restrain a battleship. "The table's strong enough that you don't need fancy hydraulic vices. Just put the work where it won't move and let the iron do its job." James checked the setup with his engineering team, measuring the casting's position relative to the planer's axis. The top surface sat 6.2 inches above where it needed to be, over 150 pounds of manganese steel to remove per linear foot. The Bibe CNC machines had attempted this removal in multiple light passes, trying to avoid the tremendous cutting forces that hard materials generated. Tommy had different ideas. He positioned the tool head for a single pass, setting the depth of cut at 0.150 inches, 10 times deeper than the CNC had dared. Sarah watched him select the feed rate using century-old change gears, choosing a combination that would move the table at 8 feet per minute while the tool carved its path. "The Cincinnati engineers understood something modern builders forgot," Tommy said, adjusting the tool height with the crossrail's hand crank. "Mass wins. This machine weighs 20 times what those CNCs weigh. When cutting forces spike, the iron absorbs them. No deflection, no vibration, no servo drives fighting to maintain position." He engaged the table drive. The DC motor's deep hum increased in pitch as the massive table began moving, carrying the turbine housing toward the waiting cutting tool. The carbide tip engaged the hardened surface with a sound like tearing metal. Blue chips erupted from the cut, each one thick as cardboard and glowing with the heat of plastic deformation. The forces were enormous, thousands of pounds pushing against the cutting edge, trying to deflect the tool, twist the workpiece, shake the entire machine. On the CNC planers, those forces had overwhelmed the ball screws and overloaded the servo drives. On the Cincinnati, they disappeared into 40,000 pounds of cast iron that barely noticed the violence occurring on its table. James watched the depth gauge as the tool completed its first traverse, exactly 0.150 inches removed across the full length. The surface finish showed the characteristic pattern of a sharp tool taking a heavy cut, smooth, consistent, free of chatter marks that indicated deflection or vibration. Tommy positioned the tool for the return pass, demonstrating the planer's fundamental elegance. It cuts in one direction, rapid traverse back cut. Again, simple, reliable, boring as hell to watch but impossible to break. But could it maintain this performance for the 40 passes needed to remove all the excess material? Hour 6. The planer had removed 3 inches of manganese steel without complaint, running continuously through cutting cycles that would have destroyed lesser machines. Tommy stood watch like a ship's engineer, monitoring temperatures, listening for any change in the machine's rhythm, checking oil levels in reservoirs that fed lubricant to the ways. James documented everything, creating a record that read like a testimony to engineering principles the modern industry had forgotten. Cutting forces measured by strain gauges peaked at 12,000 pounds during each pass, enough force to bend the ball screws on their failed CNC machines like soft copper. The planer's rack and pinion drive system, crude by contemporary standards, transmitted those forces through gear teeth, the size of piano keys, without flexing or breaking. The DC motor drew steady amperage, its wound armature converting electrical energy to mechanical power with the efficiency of any motor designed before planned obsolescence became a business model. No variable frequency drive to fail, no encoder feedback to corrupt, no software to crash. Just electromagnetic fields doing what Maxwell's equations predicted they would do, every time, forever. Sarah brought lunch to the shop floor, insisting that Tommy take a break while the machine ran unattended. "You trust it that much?" she asked, watching the massive table traverse back and forth with hypnotic regularity. "Trust isn't the word," Tommy replied, biting into a sandwich without taking his eyes off the cut. "This machine doesn't ask for trust, it just does its job. Been doing it since 1911. Probably will be doing it in 2111 if someone keeps oil in the reservoirs." The cutting tool wore predictably, carbide dulling at a rate Tommy had calculated from machinability tables published in 1960s engineering handbooks. He changed inserts every 4 hours, a process that took 3 minutes and required only a wrench and careful hands. No tool touch-off routines, no probe cycles, no offset compensation algorithms. Just measure the new tool height and adjust the cross rail accordingly. By hour 12, they had removed 4.5 inches of material. The turbine housing's transformation was visible. What had been a rough casting now showed machine surfaces that reflected the shop's fluorescent lights. James ran a straight edge across the finished area, checking flatness with indicators that confirmed Tommy's claims. 0.003 variation across 16 feet, well within specification. The night shift arrived to find the planer still running, still removing steel at a rate that seemed impossible for equipment built when the Titanic was still under construction. Word spread through the shop. The old machine Tommy had salvaged was actually working, actually solving a problem that had defeated modern technology. But the real test wasn't endurance. Could it hold precision across the final passes where surface finish and dimensional accuracy would determine success or failure? Hour 38. The final pass approached, the cut that would determine whether 113-year-old technology could meet 21st century engineering specifications. Tommy had spent the previous hour preparing, checking every adjustment, verifying every setting with the methodical care of someone who understood that precision came from accumulated attention to detail. The turbine housing had been transformed. Where 6 inches of excess material had once existed, now a flat surface emerged that showed the careful progression of cuts Tommy had orchestrated. Each pass slightly lighter than the previous, each one bringing the surface closer to final dimension, while maintaining the geometric relationships that flatness specifications demanded. James positioned laser measuring equipment, setting up verification, systems that could detect deviations measured in microns. Sarah documented the setup with video, creating a record that would either vindicate Tommy's faith in old iron or prove that some tasks genuinely required modern technology. The final depth of cut was .020 inches, light by the planer's standards, but still aggressive compared to finishing practices on CNC equipment. Tommy had selected a feed rate that balanced surface finish against productivity, choosing settings that Cincinnati's engineers had established through testing a century ago. "Here's what people don't understand about old machines," Tommy explained as he positioned the tool. "They think precision comes from tight tolerances in manufacturing. It doesn't. Precision comes from geometric stability under load." He gestured toward the planer's massive frame. "This iron was cast in 1910, aged for 6 months, machined in 1911, and has been absorbing cutting forces for 113 years. It's not going to deflect now." The final pass engaged with the same tearing sound that had characterized every cut before it. But this time, James watched the laser measurements update in real time, showing surface position relative to absolute reference. The numbers held steady, variation staying within a band of 0.003 inches across the full 16-foot length. When the table completed its traverse, Tommy shut down the drive and stepped back, letting the measurements speak for themselves. James verified the results with manual instruments, precision levels, straight edges, dial indicators that confirmed what the lasers had shown. The surface flatness measured 0.0028 inches across 16 feet. Surface finish averaged 125 micro-inches, smoother than the specification required. Dimensional accuracy was within 0.005 inches of nominal, tighter than the drawing tolerances. Sarah pulled up the original CNC programming files, comparing what the modern machines had attempted against what the planer had achieved. The CNCs were programmed for 0.010-inch depth of cut in the final passes. You took 0.020 and got better results. Tommy cleaned the tool holder, his movements showing satisfaction without arrogance. Different philosophy. They tried to avoid the forces. I let the machine absorb them. But the ultimate question remained. How much had this achievement actually cost compared to the modern approach that had failed? Monday morning, James presented his analysis to Great Lakes Heavy Industries executive team. The numbers told a story that challenged every assumption about modern manufacturing efficiency. Total project cost using the Cincinnati planer, $47,200. This included the $12,000 purchase price, $8,500 for rigging and installation, $4,200 for electrical work and cleaning, $18,000 in labor, Tommy's weekend overtime plus support staff, and $4,500 in tooling and consumables. The work had taken 42 hours of actual cutting time spread across 4 days. The failed CNC approach had consumed $340,000 in damaged equipment, created 2 weeks of scheduled delays, and still hadn't produced a finished part. Even if they had succeeded, the estimated completion time was 6 weeks of intermittent cutting, repeatedly stopping to let machines cool and servo drives recover from thermal overload. But here's what really matters, James continued, showing a calculation that made the CFO lean forward. We've got 11 more turbine housings to machine for this contract. The planer can complete one every 5 days. The CNCs, even if we repair them, would need 3 weeks each, if they could finish it all. Sarah added the strategic perspective. We bought manufacturing capability that won't become obsolete. No software licenses, no support contracts, no planned replacement cycles. This machine ran for 113 years before we bought it. It'll run another 113 if we maintain it properly. The cost per pound of material removed revealed the efficiency gap most clearly. The planer had removed 8,400 pounds of manganese steel at a cost of $5.62 per pound, including all overhead. Industry standard CNC job shop rates for difficult materials ran $35 to $50 per pound, when shops would even accept the work. Tommy presented the maintenance requirements with characteristic understatement. Oil the ways daily, change the cutting oil weekly, grease the rack and pinion monthly, check the weigh wear annually and re-scrape if needed, which probably won't be necessary for 20 years. No software updates, no servo tuning, no firmware patches. The machine doesn't know what year it is. The executive team approved purchasing 2 more Cincinnati planers that Tommy had located, a 12-foot model from a closed shipyard and a 16-foot machine from a defunct railroad shop. Total cost, $28,000 for both, less than half of one CNC repair estimate. 3 months later, Great Lakes Heavy Industries completed the turbine housing contract 6 weeks ahead of schedule, generating $225,000 in early completion bonuses. The Cincinnati planers had removed over 90,000 pounds of hardened steel without a single failure, running with the methodical inevitability of machines designed when built to last meant building so something couldn't break. James stood beside the 1911 planer on a quiet Sunday morning, running his hand along iron that had served American manufacturing through 2 world wars, countless recessions, and wholesale technological transformations that had rendered entire industries obsolete. The machine hadn't survived by being obsolete. It had survived by being exactly what manufacturing had always needed: mass, precision, and geometry that refused to quit. But now the question nobody wanted to ask had become unavoidable. If machines built in 1911 could outperform equipment designed with a century of additional engineering knowledge, what else had modern manufacturing gotten fundamentally wrong?